Hello students, welcome to this virtual classroom for 4th SEM Pass. Before lockdown I could not cover too many things on ring theory. I just took 2 or 3 classes probably. So let me start from the very beginning of unit 5, that is ring theory. So in today's lecture we will be discussing about binary operation and definition of ring, then the concept of ring with unity, then commutative ring, and I'll discuss some examples of rings. Okay, so let us begin the unit 5 of your course. So let me start with the concept of binary operation, which was already done in college. So binary operation on a non-empty set A is a function from A cross A to A. Okay, so we need two elements from A and then we operate something on that, and the result that we get is also an element of A. Okay, so if that happens, then we say that it's a binary operation. Okay, for example, plus, that is addition, is a binary operation from n cross n to n. Okay, say addition of natural numbers. Okay, if we take natural numbers, we can add any two natural numbers, and the sum of two natural numbers is always a natural number. Okay, so plus of a comma b is defined as a plus b, the usual addition that we have learned since our childhood. Okay, so it's a binary operation. Sum of two natural numbers is a natural number. Okay, it's a binary operation on the set n. Similarly, cross, that is the multiplication from r cross r to r, is defined by multiplication of a comma b. It is defined as a into b, the usual multiplication or the product that we understand. Okay, so it's also a binary operation. But there are some operations where you will not get that the product or the result of the operation is lying in the same set. Okay, for example, if you take the operation of subtraction on the set of natural numbers, then it is not a binary operation, because the difference of two natural numbers may not be a natural number. Okay, for example, 2 minus 3 is minus 1, but minus 1 is not a natural number. So what is our conclusion? The operation of subtraction is not a binary operation on the set of natural numbers. Similarly, the operation of division is not a binary operation on the set of real numbers. Okay, because we cannot divide by 0, right? So 2 by 0, 3 by 0 doesn't make any sense. Okay, so division is not a binary operation on the set of real numbers. Okay, right? So yeah, so after that, one definition that will be very useful for us, that is the definition of group, which you have already done in college. A non-empty set G together with an operation star is said to form a group if star is a binary operation on G, that is G is closed with respect to star. Okay, another way of saying that star is a binary operation is saying that G is closed with respect to star. What does that mean? Star is a function from G cross G to G. Okay, right? So so in other words, what you have already learned is A star B belongs to G for all A comma B in G. Okay, take any two elements in G, A star B should belong to G. If that happens, then star is said to be a binary operation, or G is closed with respect to star. Okay, next property that should be satisfied for the set G to be a group is A star B star C should be same as A star B then star C. That means the operation is associative. Okay, so the brackets are not important, right? Whether we operate B star C first or A star B first and then operate C, it's the same thing. Okay, so such type of property is called associative property. So star has to be associative in G. Okay, another property is that there exists an element E inside G which satisfies this condition. A multiplied with or A operated with E gives you the same value, that is A. Okay, and which is also equal to E operated with A. Okay, so the element E is called the identity element in the group. Okay, and the fourth property if G is a group, then for every A inside G, there is an element which we denote by A inverse, which is also inside G, and it satisfies A star A inverse equal to identity element equal to A inverse star A. Okay. So this A inverse is called the inverse of the element A. So if G is a group, then every element should have an inverse. Okay. So this was the definition of group. So in unit 5 we begin with ring. So a non-empty set R with two binary operations. Okay. For in case of group, only one binary operation will be there. In case of ring, there will be two binary operations. So the first binary operation will be known as plus, that is addition. Okay. And the second binary operation will be known as multiplication, that is dot. Okay. So is said to be a ring, then R with respect to plus and dot is said to be a ring if it satisfies the following conditions. Okay. What is the first condition? R is closed with respect to plus. Okay. This already we have stated because we have started with the line that R is a non-empty set R together with two binary operations. Okay. So when we say binary operation, it automatically means that R is closed with respect to that. Okay, still we write this as the first point so that we do not miss out. Okay, while checking whether a set is a ring or not, we should not miss out this very important point. Okay, that is why this is listed again. So for any two elements in R, the result of A plus B should be an element in R. Okay, so R is closed with respect to plus. Next, plus is associative in R, that is A plus within bracket B plus C is same as within bracket A plus B and then plus C. Okay, for every A, B, C in R. Then there exists an element 0 inside R such that A plus 0 is same as A, which is same as 0 plus A for every A in R. Okay, it should be satisfied for every element A in R. Okay, so A added with any element A added with 0 should give you A. Okay, so there should be such an element 0 in R. Okay, so this 0 is called the additive identity. And the fourth property is for every A inside R, there exists an element minus A inside R such that A plus minus A is 0, which is equal to minus A plus A. Okay, so the first four properties mean that R plus is a group. Okay, R is a group with respect to plus. So when we denote a group in the additive notation, A inverse is denoted by minus A. Okay, so this minus A is actually A inverse, right? A inverse is actually minus A, right? The fifth property is that plus has to be commutative in R. That means A plus B should be equal to B plus A for every element A, B in R. Okay, this is the fifth property. There are some more properties also. R is closed with respect to multiplication. Okay, so we are done with the properties of addition. Now we begin the properties of multiplication. R should be closed with respect to multiplication. So this also we have already stated that R is a multiplication is a binary operation in R. Okay, so what is the meaning? A dot B should be in R for every AB inside R. Okay. Next, multiplication should be associative in R. That means A dot B dot C should be same as A dot B dot C. Okay, for every ABC in R. Then two more properties are left. There is left distributive law and the right distributive law. So left distributive law means A multiplied with B plus C is same as A multiplied with B plus A multiplied with C for every ABC in R. Okay. Right distributive is A plus B multiplied with C is A dot C plus B dot C for every ABC in R. So if the set R together with plus and dot satisfies all these 9 properties, then R plus dot is said to be a ring. Okay, so it is to be observed that the properties 1 to 5 actually mean that the set R with respect to plus is an abelian group. Okay, right. So thus whenever R plus dot is a ring, R plus is an abelian group. Okay, so yeah, so let us come to the definition of ring with unity. Okay, so a ring R plus dot is said to be a ring with unity if there exists an element 1 inside R. So we denote it by 1. It may not be the actual one that we studied in numbers. Okay, it may not be the number 1. In fact, you will see today itself in when I do rings of matrices, this 1 will be actually the identity element. Okay? Identity matrix, right? So this one depends on the set where it belongs. Okay, so here it is just a symbol. In this case, it is just a symbol. Okay, it may not be the one that we know. So if there exists an element 1 inside R which satisfies A multiplied with 1 equal to A equal to 1 multiplied A with A for every A in R. Okay. So 1 is called unity of R, right? So every ring may not have such an element. There are some rings which have this unity element. Those rings are called rings with unity. Okay. And what is a commutative ring? Ring R plus dot is said to be commutative if A dot B equal to B dot A for every AB inside R, right? When is a group said to be commutative? If A star B equal to B star A for every AB in R, right? And here in case of ring you have two operations, but already in the definition itself A plus B is B plus A. We want the addition to be commutative. Okay, so a ring is said to be commutative if it is commutative with respect to the second operation also. Okay, by definition ring is commutative with respect to the first operation. Okay, together with that, if it is also commutative with the second operation, then the ring is said to be a commutative ring. Okay, commutative ring. Okay, now let us see some examples of rings. Okay, so actually the concept of rings and these things originated from the study of these integers, real numbers, rational numbers, okay, which had occurred naturally. Okay, so the properties are actually borrowed from these properties of integers, real numbers and all. Okay, so it's a generalization of those concepts. So in particular, the set of integers Z is a commutative ring with unity with respect to usual addition and multiplication. Okay, so that's quite obvious because the usual addition and multiplication, they all satisfy these properties. In fact, these properties are actually taken from the concept of usual addition and multiplication. Okay, so how to justify that the set of integers Z is a commutative ring with respect to the usual addition and multiplication? You just have to list the properties. Okay, so starting from 1, so it is always advisable to number the properties so that you do not miss out any of these properties. Okay, so when you write it in exam, the examiners should be able to understand that you remember all the properties. Okay, and you have listed all the properties. So please make sure. So the first property is the closure with respect to addition. So if you add any two integers, the result is an integer. Okay, that's a natural way. So sum of two integers is an integer. Just we have used that property to show that Z plus is closed. Okay, then we also know from our childhood days that addition of integers is associative. So A plus B plus C is same as A plus B plus C. Okay, then 0 is an integer and 0 satisfies this property. A plus 0 is A, which is equal to 0 plus A. 0 added with any integer is the integer itself. Okay, so 0 is the additive identity. Then for every A in Z, the quantity minus A is also in Z. Okay, if 2 is in Z, minus 2 is also in Z. Okay, so and A plus minus A is always 0, which is equal to minus A plus A. That means for every element in Z has additive inverse. Okay, then we know addition of integers is commutative, that is A plus B equal to B plus A. So commutative property is also satisfied. Then we know that if we take the product of any two integers, then it's an integer, right? So Z is closed with respect to multiplication. Then multiplication of integers is also this will be associative. I'll write the commutative property later. Okay, this has to be associative, right? It's not commutative. I mean, it's commutative, means for this particular point I want it to be associative. Okay, right? So multiplication of integers is associative, that is A dot B dot C is same as A dot B dot C. Then multiplication left distributes over addition. Okay, this is also a property. Multiplication right distributes over addition. This also is known. And the element 1 inside Z, this is the actual one. Okay, this is the number 1 that we know. Okay, so we have 1 belongs to Z and 1 satisfies this. Any number multiplied with 1 is the number itself. Okay, so Z has a unity element. Also, multiplication of integers is commutative operation, that is A star B, A dot B is same as B dot A for every AB in Z. Okay, so together with those 9 properties, it also satisfies the unity property and the commutativity property. Hence, Z is a commutative ring with unity. Okay, it is a ring because of the first 9 properties. It is commutative because of the 11th property. It is a ring with unity because of the 10th property. Okay, So here we have justified. So at home you please try yourself, almost similar, just in place of z you have to write q, that is the set of rational numbers. Okay, so the set of rational numbers is a commutative ring with unity with respect to usual addition and multiplication. So just you can justify the same way. Okay, so please do it yourself. The set of real numbers is a commutative ring with unity with respect to usual addition and multiplication of real numbers. So justification is same as above. Okay, now let us try this. The set of 2 by 2 matrices over R over the set of real numbers is, that means the entries are from real numbers, is a ring with respect to usual addition and multiplication of matrices. Okay, so justification, let M2 be the set of 2 by 2 matrices over R. So if we have two 2 by 2 matrices, say A, B, C, D and E, F, G, H, their sum is defined this way, element wise addition, right? So this is also a 2 by 2 matrix. So the M2 is closed with respect to addition. Okay. Then we know matrix addition is associative. Okay, by properties of matrices that you have studied in higher secondary, matrix addition is associative, and you can prove it also. It's simple. Okay, then 0 0 0 0, all entries 0. This is called null matrix. Okay, and null matrix always satisfies this. Any matrix added with null matrix is the matrix itself. Okay, so 0 0 0 0 is the additive identity in M2, right? Then for any ABCD inside M2, we have, if you multiply those elements by minus 1, minus 1, minus 1, okay, then you will also get an element in M2, okay, because M2 is the set of all 2 by 2 matrices with real entries. So if A is a real number, minus A is also a real number. If B is a real number, minus B is also a real number. So this is very much an element inside M2. And if you take the sum of these two, you will get the sum as 0. Okay. And number 5 property, we know matrix addition is commutative. Okay. Number 6 property, the product of 2 by 2 matrices is a 2 by 2 matrix. Okay. So you can just find the product and then say. In fact, it's not necessary to find the product also. If we multiply a 2 by 2 matrix with a 2 by 2 matrix, the answer is a 2 by 2 matrix. Okay, by definition of the product. Okay. So we know matrix multiplication is associative. This is also a standard property in matrix theory. We know matrix multiplication left distributes over addition. Okay, all these are properties of matrices. So we are just listing out. Okay, we know matrix multiplication right distributes over addition. Okay, so A into A plus B into C is AC plus BC for all ABC inside M2. Okay, and let I equal to 1 0 0 1. So up to ninth property we are done with the fact that M2 is a ring. Okay, next let me show that M2 is a ring with unity. Okay, so what is the unity element? Obviously the identity element, identity matrix. Okay, so then I belongs to M2 is the identity matrix, and we know by property of identity matrix, any matrix multiplied with identity matrix will be the matrix itself. Okay, of course the order has to be same, right? So A is an element in M2 and I is the identity matrix. So A into I will be A, which is same as I into A. So M2 has unity. Thus M2 plus dot is a ring with unity. Yeah, but it's not commutative. Okay, it is not a commutative ring. Why? Because matrix multiplication is not commutative. Matrix addition is commutative, but if you multiply two matrices, the order is important. AB may not be equal to BA. In some cases it is equal, but in general AB is not equal to BA. So you can consider these two examples, very simple examples. A is 1 0 1 0, B is its transpose. Okay, so even A and A transpose may not commute. Okay, so but AB is what? 1 0 1 0 1 1 1 0 0. Okay, so if you take the product, 1 multiplied with 1 plus 0 multiplied with 0, right? So this is 1. So it's the matrix 1 1 1 1. But if you take it the other way, 1 1 1 0 0 multiplied with 1 0 1 0, in that case the product is 2 0 0 2 0 0 0. Okay, so AB is not equal to BA, right? So the set of 2 by 2 matrices is not a commutative ring. It is a ring with unity, but it is not a commutative ring. Okay, so this is how we justify. So at home, please you try this this generalization, the set Mn of n by n matrices. Okay, I have done the case with 2 by 2 matrices. You do the same thing with n by n matrices. Okay, you show that it is a ring with unity with respect to usual addition and multiplication. Okay, so you try to justify, find the unity element, find the zero element. Okay, just try, and also try to show that it's not commutative. Okay, and another example, the set C equal to a plus ib, where ab belongs to R, of complex numbers. Okay, is a commutative ring with unity with respect to usual addition and multiplication of complex numbers. Okay, so this also you try to justify. Okay, so till in the next lecture I'll deal with some more problems. Thank you.